welcome to the next lecture in the video lecture series of the course Operating System. In this lecture, we'll be talking about the concept called threads. So far in the course, we have discussed extensively about a concept called process. We saw how processes are created, how operating system provides different APIs to work with processes, and in the last two lectures, we saw different process scheduling techniques. The whole discussion about processes revolved around a concept called multiprocessing, where the basic idea was to allow more than one process to be executed on the CPU. And how did these processes execute? They executed in a time-sharing way. That is, for some portion of time, the one process got executed, then it was taken out, and the other process was given a chance to execute. When did this happen? So whenever a process got blocked, that is, it requested for some I/O, we say that the process goes into a block state. Those processes were taken out from execution, and the CPU would then start executing some other process. So that was the basic idea of multiprocessing. And this movement of process from the CPU to the ready state and back from the ready state onto the CPU execution, that's what we call context switching. So this swapping in and swapping out of processes from the CPU execution mode is what we call context switching. But context switching comes with a certain overhead. Some additional time is spent in doing some work whenever there's a context switch. What is that? So whenever a process is taken out of execution, its states need to be saved. Because when it was executing on the CPU registers had some values which were stored. I mean, whenever a process is taken out of execution, those values which are currently held in the CPU registers need to be saved. That's what forms the state of that particular process. So whenever a process is swapped out, its states need to be saved. And similarly, whenever a process is swapped in, that is, a process now is going to be executed by the CPU, its states have to be loaded onto the CPU registers. So this swapping in and swapping out process involves a lot of state saving. The amount of time that is spent in saving these contents is what we call the context switching overhead. And that's a very costly step. So as far as possible, the idea would be to reduce this context switching overhead. Now, if multiprocessing is an advantage because it allows multiple programs to be executed in a time-sharing way, we try to argue whether multiprocessing is beneficial in implementing parallelism. That means, if you would like many applications to run at the same time, can multiprocessing be beneficial in this case? Let's look at a situation. Now say we have a web server or a file server. So let's consider a web server or a file server process. So say this is the kernel space and this is the user space. So this is the kernel, and let us assume that in our system there is a particular process which is a web server. Web server means it's some kind of a process that is running in your system that will be able to provide certain web services. There can be a lot of web services. Let's say this particular web server is allowing some web service. Or it can be a file server. That means it contains a lot of files. If a request for a certain file is, a particular file is requested to this server, the particular file server process would grant or provide this particular file to the program that has requested for it. So there can be, so this is the web or file server process. Now, this runs a certain code. And let us assume that a particular client, this is another program, that is requesting for a web service or some file. So it puts its request, and depending on whether the request is genuine, that particular web service or the file service, it grants or provides that particular file or the service it is provided to the client. Client is another program that is requesting for the service, and the service is provided by the file server or the web server. Okay. Now, as long as there's only one single client, it's okay, because it's just that the service has to be provided to that particular client. Think about a situation where there is more than one client. There's one more client. Say this is client number 2 that has again put a request. Now, in order to parallelize this, the idea would be that this service, the idea of providing this service can be distributed among these two clients. Okay, that would obviously increase the efficiency of a system if you can parallelize and address these two clients simultaneously or in a parallel way. But how will this be possible? This is only possible if this file service, which is this program, creates a copy of it, and then the copy which is being created will now service one of the clients. So it's like this. Suppose there's one more client that has requested. Now what this particular process would do is, it will create a child process. Okay, so this kernel, it requests for this kernel by using a system called fork, and a child is created. Now this child would also be the exact replica of the process which was its parent. That is the process that was created from here. And now instead of this client 1 servicing this, the service would now be provided by the child to the client which has requested. So client 2 would be served not by the parent but by the child. So that's how, by using two processes, that is from using two web servers, two clients can be addressed at the same time. Seems to be a very valid solution, but there is some problem with this. The problem is that if you have multiple clients and you want multiple clients to be addressed simultaneously or parallelly, then you need to have those many copies of the web service or the file service. So that is, you need to have those many copies of the process that was executing. Okay. And we already know that every process has a corresponding memory image associated with that. So if you have multiple such copies of the process, for each of those copies you will have a certain memory image. Okay, and thus you will end up into two problems. The first problem would be that you will have a large amount of memory is occupied for all the web server processes, web servers. So for each of those copies that you create, you have a certain amount of memory that is occupied. So if there are n such clients, this solution allows you to have n such copies of the web server, and which means for each of them you will have a certain memory image, and you will have n such memory images, and that will consume a lot of memory. So that's the first problem that you will have. The second problem is the information sharing between processes is possible. Okay. We will talk about this in our next lecture when we will talk about inter-process communication. But for the time being, let us assume that if two processes have to communicate, so if these two have to communicate, then that's a very costly process, because there are a lot of information exchange between two processes which are residing at two places in the memory. Remember, each process has a different memory image. So that means the data transfer or whatever be the communication between these two processes actually comes down to communication between two separate memory images. And that's a very costly process. So we'll talk about how this problem can be solved. Okay, so for the time being, These are the two basic disadvantages that we find if we go for this multiple processes, creation of multiple processes, and each process catering to each one of those requests. So what is the better way than this? So a better solution would be that instead of creating a separate process, if you could break the stream of execution of a single process, and once the stream is broken, you create a number of such streams and you divide the work among the streams created of a single process. So the idea is that by default, one single process has a single stream of execution. So each process has a single stream of execution. Okay. So if this is the process, this is my stream of execution, and let me call this stream of execution as a thread. Okay. So that's the code that I would like to execute. So let's go back to that web server. That's the single, the web server process. By default is one single stream or one single thread that needs to be executed. So this is what happens when the process starts. But as the process starts executing, it can give rise to multiple such streams of execution. It means, so as the process executes, it can create multiple streams of execution. And this is a very interesting thing to consider. That means, so later on, this process would eventually give rise to multiple such streams of execution. This is this single execution that started when the process was created initially. Later on, it can give rise to different streams of execution, or each one of them is called a thread. So you can have multiple threads now. Okay. So if we have split it up, this single stream of execution into multiple streams, now we can make use of this multiple streams and divide the work among these streams. So it's like this, that now instead of having two streams, let's go back to the web server and see how this can be beneficial. So the idea is, previously we saw that we had a concept where if this is one process with a single stream of execution, it actually forked and created another process, and now this was addressing a process called client 1, and this was addressing the request coming from client 2, and say this is our web server. Okay. So now this is the kernel, this is the user space, this is the kernel space. Now our solution now is, since a single process can create multiple streams of execution, there is no need to create a separate process. Rather, what we can do is, let's look at the situation here. So the idea is, this process now will have multiple streams of execution, and each one of them will now be taking care of the request coming from each one of the threads. So this is the basic idea. Okay. So let me explain the same thing with a different application that may be helpful again. So instead of web server, you may consider it to be, let's say, some kind of text editor. Okay. So let's say we have a text editor, and this text editor now has 3 jobs to perform. One is, let's say, we would like to have a text formatting. We can have auto save of the documents, and you may perform an automatic spell check. So now you have 3 jobs, and you would like these 3 jobs to be done parallelly. So the first solution would be that each one of this text editor process would create 3 such copies of itself, and each one of them would be working on each of these 3. You divide this work in among these 3 processes which are created. The other solution would be that instead of creating 3 processes, you divide this text editor process, you create 3 multiple streams out of that. That is 3 threads, and you allow, or you divide this work, the 3 different work that you would like, and allocate them to each one of those streams. Okay. So you see, by making use of this multiple thread concept, you could bring about parallelism. So all these 3 work can be parallelly executed by these 3 streams. So what is the advantage that you get by this multi-threading concept? So the advantage that we have is the following. Number 1, as you see, we are not creating a separate process. Rather, the executing process itself gives rise to 3 different streams of execution, which means the threads or the streams of execution are born out of the process. Now, since threads are created out of processes, okay, it obviously means that all threads, they share the same memory image of the process. That means they lie within the same address range allocated to a particular process. You don't have any separate memory image for each of the threads, which means no additional space you require for this particular threads. That's the first advantage. Remember the problem that we discussed, that every process is an individual entity, so it occupies a certain memory image. As a result, each new process that you create, you have an additional memory space to be allocated. But in this case, each thread is a part of the process, so the entire memory image that you create is part of, the threads are part of that. So you don't have any additional space for each of the threads. Okay, most importantly, since they are born out of the process, since threads are created out of the process, they share the code and the data of the process. That's very, very important. Okay, just that we split this up into 3 streams of execution. The overall code is still the same. Look at this. The process is still the entire text editor. Okay. Or it's the same web server. Just that you split it up. You allow these 3 streams to work on different portions of the code. The code is same for each one of those streams. The difference is that the particular stream is executing on different portions of the code. That is important. So since the code and the data is made available to each one of them, okay, so it's very easy for them to communicate. So it means the information sharing among threads is easy. Okay, and the reason why, because of these two advantages that you have, okay, you often call threads to be lightweight processes. So it feels like it's very similar to how processes work. They are very similar, except that they are much lighter. They're not bulky as compared to processes, because processes have a lot of, a lot more number of things as compared to threads. Okay, so let's argue on this fact. Okay. So we understand that threads are nothing but the stream of executions which are created out of a process, and this stream of executions created from a process share the code and data of a process. They lie within the same memory image as allocated to that particular process. Because these stream of executions or threads, they share the code and data, that is the reason why the information sharing between these threads is very quick. You do away with a lot of overhead that is usually present when we have inter-process communication. And the threads, because they are created out of the process, they share the code and the data. So let's look at what exactly is the memory image looking like for multiple threads. So it's something like this, that if we look at the memory image of a process, so we can assume that there's some portion which is common, and now if these are the three streams of execution which have been created out of this process, now these three streams of execution, they share the code. Okay. So you can consider the same text editor example. So if this process is the text editor that is running, or the browser, and all the tabs that you create when you open a new tab, what you're actually doing is you're creating a new stream, you're creating a new thread, and each of those tabs that are open for your browser are nothing but these streams, these threads. So each thread is able to access the same code of the browser or the same code of the text editor. Okay, so the code is shared by each one of them, and there is some data which is also shared. If there is some files with which your process is working with, the files is made available to each one of those threads. However, there are certain executions, because every thread is working at, so the threads, they share the code and data, but they work on different portions of the code. So this is important, right? So you may wonder, this is working on the autosave mode of the text editor. This is maybe working on the spell check portion of the code of the text editor. So because they are working on different portions of the code, it is obvious that they would generate some temporary data. I mean, the state of these particular threads would be different. Okay, so this implies that they will have different states. Okay, so if they have different states and you would like to switch between the threads, in that case, those states of the currently executing thread has to be saved. So when a particular thread is working and you want to switch to execution of a different thread, then the state of the thread has to be saved, right? And where will these states be saved? Obviously, they will be saved in some stack area. So that means every thread must have a unique stack area. So each thread has a separate stack where it saves the states the moment there's a context switch between the threads. What else? Now, as we said that they have different states, and the states is actually governed by the content of the CPU registers. important registers such as program counter, stack pointer. The values of these registers define the state of a particular thread. Now, if that has to be saved, so then the register contents, they have to be unique for that particular thread. Okay. So if this is a particular thread which has resulted out of this process, this entire thing is, let's say, a process which supports multi-threading, and we have created 3 threads out of that. Each thread will be sharing some code and data and files. However, the ones which would be unique for a particular thread will be its stack and some registers. So this is this. Each thread will have its own stack and registers. So is the view of how the how the threads work and how they share the resources of the process which gave rise to these threads. Now, threads represent a separate stream of execution, right? So that means that when one thread it gets blocked, the other executes. So this is the idea behind applying multiple threads. That if one of the threads, you can create a number of streams of execution, but they are independent. That is, if one thread is blocked, it does not affect the other one. The other can keep on continuing. Now, since these threads, they happen to work independently, so this means that every thread needs to save its state, right? And we've already seen that in case of process, that the states or the information about an executing process is maintained in a data structure called the process control block. So recall, so in case of process, we had used something called the process control block, or we in short call it the PCB. So what is this PCB? Whenever a process is created, the kernel, it maintains a data structure which holds information about the process which has just been created. What is present in this data structure? Lot of information, such as the process ID of that particular process, the process ID of the parent of the process. Then we have information about the scheduling of this particular the schedule. We have information about the memory management. Okay. Then we have information about the files which are there. And we have pointer to the kernel stack. So all information regarding the process is maintained in this data structure called process control block, and the kernel maintains it. So here we have, let's say this is the process that is being created. So information about this is maintained in the PCB, and you see here it's a table of all the processes. So if there are 1, 2, 3, 4, so let's say there are 4 processes which are currently present in the system, and the kernel keeps track of all the processes by maintaining a table of the PCBs, and that's what we have. That's the way in which the kernel keeps track of all the processes. Okay. Now, the moment the process terminates, the PCB is removed. Okay, and the process allocated for that is reclaimed by the operating system. So that is how the kernel keeps track of the processes which is there in the system. Similar to that, the threads also maintain their status in something called the thread control block. And we call it the PCB. So pretty similar to how the information about processes is maintained in process control block. The information about a thread which has just been created is maintained in something called the thread control block. Now, usually, if the process, if the threads happen to run only in the user space, okay, then the thread control block is maintained by the process itself. So this is the process that has created these threads. So information about these threads is maintained in a data structure called thread control block, and this is the table that contains thread control blocks of all the threads present here. So this is called the thread table, pretty similar to how kernel maintains the information about all the processes in this process table. So all the threads which are created in this process is maintained in this thread control block, and this is a table of which contains the thread control blocks of all the threads. Now this is one situation where if the threads are created in the user space, okay, so that user space created threads or user libraries created threads, so the thread information or the thread control block is maintained by the process. Just that there is a pointer that links this thread control block to the process table, so that the kernel through this process table would actually have a link to the threads. So the kernel doesn't know about the threads, but it maintains an information about the process. So the information that how many threads have been created in this particular process, to maintain that information, there is a pointer linking the threads corresponding to the process entry in this process table. This is how the threads created in the user space is linked to its information maintained in the PCB of the corresponding process which has created the threads. This is one situation. Okay. This is the situation where the threads are created in the user space. The kernel has no idea about the number of threads that has been created. It's all in the process which is running in the user space. Now the other situation is where the kernel also supports multi-threading. So it also allows a number of threads to be created. Okay, so these are called kernel level threads. In that case, the kernel maintains the thread table because it's the kernel that can create multiple threads to be generated. It can create multiple threads. So obviously the information about the threads that are there is maintained in the kernel itself. So here we have a thread table that is maintained in the kernel. So these are the two situations in which the thread tables are maintained. Either it is maintained in the process, if it is user level created threads, or it is maintained by the kernel if it is the kernel level threads. More of that we'll talk about when I'll come to the mapping of the user level and the kernel level threads. So these are the two situations, and to summarize, whenever a thread is created, the information about the thread is maintained in a data structure called thread control block, and the thread control block either resides in the user space that is within the process maintains the thread control block, that is information about all the threads, or it is maintained in the kernel if the threads are kernel level threads. Now if this is a kernel level thread, it's okay, the kernel has information about how many threads are there and because it maintains the data structure. But if it is user level thread, the kernel has no idea about how many threads are created. It's kept tracked by the process itself. However, since the kernel maintains a PCB which is an information about the process which is created, within the PCB entry, that is the entry of this within this particular process table, you will have entry corresponding to the thread control block maintained in the process. That is the difference between the two situations. Okay, now let's look at how threads are implemented. Now, Posix provides different APIs for creating and managing threads through the pthread library. And here we have the different functions that we'll be using to understand how to work with threads. The first one is a function called pthread_create, which is used to create a new thread. So this is the syntax of pthread create. It takes 4 arguments. First is the thread identifier, which is of type pthread_d defined in the pthread library. Then we have the attributes to that particular thread, followed by the start routine of the thread. So whenever you want that particular thread to execute, which is that particular code which would be executed. A pointer to that is referred here. And then this is the arguments that you pass to the thread routine. So these are the 4 arguments that we would need to pass to the pthread underscore create function in order to create a thread. We'll see usage of that with a code. Next is to destroy a thread. So whenever you would like a thread to terminate, so you would use something called pthread underscore exit. This terminates a calling thread, the thread which has been used, which has been created. And what you do is, so it's pthread underscore exit, and you pass the return value. So this is the return value. So that would terminate the thread. Okay. Then, pretty similar to how you use the wait system call in case of process, here too, if you would like certain thread to wait on another thread, in that case you use a function called pthread underscore join, which waits for a specific thread to exit. So this is the syntax of pthread underscore join, where we pass 2 arguments to that. One is the thread ID, the thread identifier on which you would like to wait for, and then the return value. So these are the 2 arguments required for the pthread underscore join. And then we have a function called pthread underscore yield, which releases the CPU to let another thread run. We have pthread attribute initiate. This is create and initialize a thread's attribute structure, and one to remove that, which is called the pthread underscore attribute destroy. So these are the 6 functions that we'll be using to understand the working of threads. I repeat, this is again a typically Posix based APIs. For different other operating systems, you may have different other functions. Okay. So we'll be strictly restricting ourselves to usage of these library calls. Okay.
Look at the implementation of the Posix based APIs for thread management provided through the pthread library. So here we have written a simple code that intends to create 2 threads, and each of the threads which get created would execute this piece of code. So each thread would print, hello, I am thread number, followed by its thread ID. So this is the routine that each of the threads should create. We intend to create 2 threads, so we have defined something called num underscore threads, and we initialize that with the value of 2. Since we are going to use the functions defined in pthread library, we include pthread underscore h. Okay, and now this is the main thread that would be creating 2 other threads. So to do that, we declare a variable called threads, whose size is given by num underscore threads, and each is of type pthread underscore t, a data type again declared in the pthread library. Okay, so the main thread would iterate 2 times, and in each of the iteration it is going to make use of this pthread underscore create function, where it will be creating a thread. Okay, so for each of the iterations, it is going to create a thread in each. And so let's recap what we how a pthread underscore create works. So pthread underscore create is a function that creates a thread. It takes as an argument the thread identifier, which we pass in this case the index of the threads array, followed by an attribute of this particular pthread underscore create, which we don't have any attribute to pass, so we write it as null. Then next is the pointer to the routine that this particular thread which is created should execute, so which in this case is print underscore hello. This is the routine that should be executed by the thread that is created, and we pass as an argument to this routine the value of I. Okay, that is the iteration number. So this is the pthread create that will create a thread, and it will return an integer that we store in a variable called status. We may check this value of status whether it is 0 or 1 depending on whether the pthread create has successfully created a thread or not. Okay. Now, once the main thread comes out of this loop, it is supposed to print this string called exiting main before it exits. So before the main thread exits, it's supposed to print this line. Okay. Now in this routine which our thread is supposed to execute, we have used something called prethread underscore exit, which, if you can recall, is a function to force the thread to terminate. So whenever a thread is created, the thread should print this line and will be terminating. Okay. Now let's look at the execution of this code. So we compile this file called thread underscore example.c, and we attach or link the pthread library by a command -l pthread. Let's run this. So we have /a.out, and there you go. So let's try to understand what the output is generated. So the first two lines, I am the main thread and the new thread created has ID 0, again the same line with my thread ID 1. So these two lines come from the main thread. So that means out of the three threads, there are three threads in total: the main thread, thread number 0, and thread number 1. These two threads are created by the main thread. So out of the three threads, obviously the first thread that gets scheduled is the main thread. So the main thread starts executing first. It enters the loop, prints the first line, creates the first thread, that is with thread ID 0. But before the thread ID 0 could be scheduled, it's still the main thread that keeps on executing. So it iterates. In the second iteration, it again prints the same line. Main thread and the new thread created has ID 1. It creates a new thread with ID 1. But before the main thread could execute, exit, thread 0 is scheduled now. Thread 0 executes this routine. Okay, so it prints hello, I am thread number 0, as you can see in this line, and then the pthread underscore exit forces thread 0 to terminate. Thread 1 gets a chance to be executed. Thread 1 also executes the print underscore hello routine. It prints hello, I am thread number ID 1, and it exits. Now again the control comes back to the main thread. The main thread prints the last statement, exiting main, and then it exits. Let's look at a second execution. Here we have a different set of outputs. Now the output itself tells you the order in which the scheduling was done. The first two lines says that the main thread started executing first. It ran through the loop, created the two threads, and then the control was transferred to thread number 0. Thread number 0 printed this hello, I am thread number 0, this line. The control came back to the main thread. The main thread moved on to print this exiting main line, and then the control switched to thread number 1. Thread number executed the print underscore hello routine. It printed this line, and then it exited, and then the control came back to main thread, which exited them. Okay, so let's run it once more to find. Okay, so here you see it's almost the same as the previous execution, the same as that. Okay, almost same. Okay, here you have a different order. So okay, now this is interesting. In this you find that the first two lines is obviously the one printed by the main thread. Then the control switches to thread number 0. Thread number 0 executes print underscore hello routine, and it exits. But this time, before the thread 1 could execute, the control switches back to main thread. Main thread prints this exiting main, and then it exits. Since the main thread exits, thread 1 now doesn't get a chance because it is forced to exit, because its parent process, the one which it was created from, has exited. So it is forced to terminate. This is the problem with this code. Okay, that is, somehow if a particular schedule make or allows the main thread to exit earlier than the two threads, which in this case is thread number 1, so that threads will never get a chance to execute. So the solution to this problem is that the main thread should wait for the other two threads before exiting. And the way to do it is by use of something called pthread underscore join. We already know that pthread underscore join works pretty similar to how wait command works for process. So pthread underscore join is a function which ensures that a particular thread would wait for some other thread. So the first argument is the thread on which the main thread should wait. So in this case, let's say it's thread 0 in which, and we are not going to pass any other value to that, so let's put it as null and say we save it, and let me recompile. Okay, now you see this is the output of the modified code, and the interesting thing to note here is that since the main thread is waiting on thread 0, we are at least sure that thread 0 would be executed under all circumstances. So main thread is the one that gets to schedule first, but after it creates thread 0 and thread 1, it has to wait until thread 0 completes its execution. So by forcing main thread to wait on thread 0, we have at least ensured that thread 0 will be executed, only then main will exit. So thread 0 in all cases would definitely be executed. We are not sure about whether thread 1 will get a chance to execute, because it may not, because it does not, the main thread does not wait on on thread 1. Okay, so this is what we have. Now, in order to execute, in order to say, let's try it once again. You see, okay. So this here ensures that the two threads would execute and then the main thread. So here we have at least ensured that main thread would be waiting on. So let's repeat the same thing for, say, thread 1, and this would at least ensure that the main thread waits on both of them. Okay, so by forcing the main thread to wait on both of them, we ensure that both the threads, they get executed, only then the main thread would exit. Okay, so this is an example to show the working of threads, and as you see in this example, we utilized 4 pthread library functions. One is pthread underscore create to create a thread. We used pthread underscore exit in order to terminate a thread. Then we used pthread underscore join for forcing a particular thread to wait on a certain thread, and we used this pthread join twice in order to force this main thread to wait on both thread 0 and thread 1.
Okay, so to summarize, we have seen what are threads and how threads can be beneficial to implement parallel execution of code. So what we found is, for a thread to be created, you need at least a process, because by default a process is a single thread of execution. So processes give rise to threads, multiple threads, and then the work is divided among the threads which have been created. So if we try to compare threads and processes, we find that threads, they don't have any data or heap. However, processes have code, data and heap. Okay. You need at least one process to give rise to a thread. So that means a process is always attached, a thread is always attached to a process. And in case of process, a process by default has a single stream of execution. So that means threads cannot live independently. They need to be attached to at least one process. However, on the other side, we say that whenever a process is created, there is at least one thread that gets associated automatically with the process. So by default, the process is a single stream of execution. Threads can be more than one. You can have multiple threads in a process. Whereas for in terms of process, these threads, they share the code, files and the I/O of process. We have already seen that. However, they have their own independent stack and the registers to save the contents, the states specific to a particular thread. So whenever a thread dies, the stack which is specific to that particular thread is reclaimed, whereas when a process dies, all threads associated with that automatically dies. So that's difference between the threads and the process. Now the question that needs to be answered is, now who manages these threads? We saw how we can make use of the pthread library to work with threads. But that's one side of the story. I mean, this is the use of pthread library is a user-defined way to manage the threads. There is one more way, which is called the kernel level threads. So the thread management can be done in two ways. Either at the user level, we saw the different codes in which the pthread library was made use of. So in case of user level threads, the user level library is used to manage threads. A typical example is the pthread library that we use. Now, interestingly, the kernel has no idea of the threads. So this is a very interesting thing to know. The kernel is completely unaware. The user process has applied or used a library and it has created a certain number of threads. The kernel is completely unaware of how many threads has been created, or there have been threads which have been created. It doesn't have any idea. Okay, so this is one way of handling things. Make use of a library in the user space or in the user process. The other is we have kernel level codes. So that means these are threads which are directly supported by the kernel. And kernel knows. So kernel actually creates these threads. So let's try to find the pros and cons of the both strategies. So first, let's talk about the user level threads. We already have seen a glimpse of that when I was discussing about this, the thread control block. Remember? So this is, say, the kernel. Okay, and here we have, this is the user space, and we have a certain process that has made use of certain user-defined libraries, say a pthread library, and it has created a number of threads. So the kernel is completely unaware of this. Okay. Obviously, the information about the threads is not maintained in the kernel. Rather, the thread control block, the TCB, or the thread table, you can say, it is maintained in the process itself. So this is the process. So what is the advantage of this kind of user defined? The advantage is, so let's first talk about the advantages. The first one is no system call required. Yeah, because you're not making use of the kernel. So since no kernel services is involved here, obviously creation of threads, unlike the creation of process which involve the fork system call, in case of thread creation, you don't need any system call if you are using these user level libraries for creation of threads. So if you're using the pthread library, we simply use the pthread_create function, and that's not a system call. So you don't need any system calls. So it's very simple to create and manage. Okay. Then since kernel has no idea, so even for cases or for you can make use of that. So can be implemented for OS which do not support multi-threading. So even if your operating system does not support multiple threads to be created, you can still implement this because you are implementing it in the user space. So because kernel has nothing to do with the number of threads which are created, so there is no problem. You can create even in systems where the kernel does not support that. Okay. Then you may wonder, then why do we need, if you don't execute that in the kernel, so there is no point in implementing or exploiting the parallelism. So why do you need that? No, it often needs, is needed for the coding purpose. Suppose you would like to implement or incorporate parallelism while you are designing the software or you are coding. In that case, you would like to divide that particular work into a number of modules and be implemented, or you would like them to be implemented as separate execution streams. So in that case, it's very suitable to make use of this kind of multi-threading concept. Okay, then because you don't require the kernel, so the switching between these threads is very fast. Yeah, because you don't have to change your mode and go to the kernel and that. So it's a very fast switching between the threads. Okay, but nothing comes for free, and so there are a few disadvantages of having the user level threads. So what are the disadvantages that we have? And the disadvantages, the first one is that the scheduling can be an issue, right? Why? No. The problem is if you have a certain thread that gets blocked on an IO and the other is runnable. So let's say in case of one thread, okay, it gets blocked on an IO and the other is runnable. Now here is the problem. What to decide? Should we go ahead with the process or should we wait for that IO? So in that case, you will have a severe problem. Okay. Then there is a lack of coordination because lack of coordination between the user threads and the kernel. So you see, if because the kernel is completely unaware of the number of threads which are there, and now consider the situation where you have two processes. One process that has a certain number of threads, and then we have another process that has a single thread. Let's say there are 1,000 threads which are created by this process, however this process only has a single thread of execution. Now the problem that happens is during scheduling. Suppose both these processes, they are scheduled according to the round-robin scheduling technique, where there's a certain time slice allocated for each of the process. Now in that case, these 1000 threads, the time slice, the computation for the time slice will be 1000 threads for this process. However, there's only one thread for this process, and that's that's the disparity that happens because the kernel is unaware. So the problem is that the same time slice is allocated to this process which has 1000 threads, and the same time slice is allocated to this process which has a single thread. A better approach would have been that you give a bigger time slice to the process with more number of threads and a lesser time slice to the process with lesser number of threads. But since the kernel is unaware of that, this is the lack of coordination between the threads and the kernel. That's the problem. And then we have, it requires a non-blocking system call. Now it means you have, if a certain thread invokes a system call, then all other threads have to wait. So that's a problem with this kind of approach. Okay. So these are the three basic disadvantages associated with the user level thread management. So if you are creating threads using a thread library in the user space, you may have a scheduling issue. Then because there's a lack of coordination, the kernel is unaware, so the same time slice will be allocated for a process with more threads and a process with less threads, because the kernel is unaware of the information about the threads. And finally, we saw that if one of the thread waits for an IO, all other threads get blocked. So that is the problem with user level threads. So what is the solution to that? So the solution to this problem is, a different approach is where you have the kernel level threads. That is, the kernel supports the usage of threads. Okay. So it's something like this, that you have, say this is your user space, and now what I did not mention in the previous cases. So if you go back to that, okay. So let me complete the user space, user level thread management. Complete this portion, then we come to the kernel. So what we said is you have multiple threads created here, and interestingly, what I did not mention is, if you recall, when we were talking about the thread control block, I said that because the threads are maintained by the process, kernel has no idea of that. So obviously, the information about the threads, that is the thread control block or the thread table, whatever you call, is maintained in the process. Right? The only way that these two are related, the data structure called the process table, which is maintained by the kernel. So you have a pointer pointing to the corresponding entry of the process in the process table. So if the kernel is maintaining the information about this particular process P in this entry, then this thread table should have a corresponding pointer to this particular entry in the process table. So this is how the process would keep track of how many threads have been created in the process. So this is what happened in the user level. Now let us move towards the other kind of thread management, which is kernel level thread. And here, interestingly, the picture is something like this, where the kernel is aware of, or it supports threads. Okay, so because it supports threads, in addition to the process table, the thread table is also maintained in the kernel. So the kernel also maintains, the kernel in this case maintains the thread control block, which keeps information about the threads which have been created. And so the processes now would be creating number of threads. Kernel would also support creation of a number of threads. Okay. Now, what is the advantage in this case? So the advantage is, in the user level thread management, we saw that there was a lack of coordination between the kernel and the user level threads. As a result, the kernel would allocate the same time slice to both processes having more threads and processes having less threads. Now, in this case, the advantage is that the scheduler will give more time to processes with large number of threads. And the second problem is, we saw that in case of user level thread management, when one particular process block or one thread makes and goes into a block state, other threads also have to wait. Now in this case, it's this is advantageous. Why? Because the kernel supports multiple threads. Even if one thread blocks, the kernel may allow the second thread to proceed. So in this case, you will have this kind of approach is good for applications that block frequently. So this is one of the advantages that we have, and the few disadvantages that come with this kernel level thread management is, as the first one, so the disadvantage that we have is, now PCBs have to be maintained, okay, in the kernel. So that's an overhead, because the kernel now keeps the PCBs, the thread table, etc. So that occupies space, that's an overhead. And the second problem is, the kernel level threads are slow, and they ought to be, because you're invoking the kernel. So because it involves kernel invocations, so these threads are slow. So now we find that there are two ways of thread management. Either you create threads in the user level or in the user space by making use of some thread creation libraries, or the kernel supports them, right? Now, since we have two kind of management, the problem that happens is, will these threads be executed as independent entities? So will the scheduler be, so we put this question and then we come to okay, so the question is that we found there are two thread management techniques. Either you make use of the user level thread management by making use of the thread libraries, or the kernel supports them, the kernel level threads. So these are the two techniques that we found. So the question is, now, do these threads schedule as independent entities? What do you mean by that? We mean, we found that kernel also supports certain threads and users can also create certain threads. Now, when it comes to scheduling, the scheduler, which is part of the kernel, that will schedule the different threads, right? Now, will it treat these threads as independent entities? That is only possible if you have certain kernel level threads. If the kernel supports different threading, okay, which means now how will you map the user level threads to the kernel level threads? Okay. So, or you can put it in this way. You can reframe that. Do this in or are they map to separate entities, that is separate threads in the kernel. So you see, now we have a problem. Problem is that a user level process has created a certain number of threads. Okay, and so this is the user space. You can see this is say the user space, and this is the process. And the kernel is also allowing certain threads to be created. So the question is, will these processes be mapped to these as separate entities? That means, will there be a one-to-one mapping of each thread in the user process to a thread in the kernel process? What will be the procedure? Now this is OS specific. So there are three different techniques which different OS they the OS they have their own choices. So the three different ways in which this mapping can be brought about are: number one, you can have a one-to-one mapping as we see here. So that means if the kernel supports multiple threads, okay, if a kernel supports multiple threads and a process has created multiple threads in the user space by making use of some user libraries, your mapping could be a one-to-one mapping. That is, each thread in this user space can be mapped to a unique thread in the kernel. So this is a one-to-one mapping. Now this is a very suitable technique for multiple processes. So it's very suitable for multi-processor environment. Linux supports a one-to-one mapping. So it supports, as it's Posix compliant, it allows user level libraries to create threads, and the Linux kernel supports multiple threading. And the mapping between the user created threads and the Linux and the kernel level threads is one-to-one. This one-to-one mapping is very suitable for multiple processors. Now, apart from one-to-one, some operating system or some kernels, they okay. So let me. So what is the disadvantage? The disadvantage is it's very costly. That is a disadvantage of one-to-one mapping. Now, in addition to this one-to-one, there is one more, which is called a many-to-one. Now, this is something like this. You may have guessed it by now, that kernel does not support multiple threads. It has only one stream of execution. However, at the user space, you can create as many threads as possible, but each one of them will be mapped to a single thread of execution in the kernel. So this is many-to-one mapping. So as you can see, this relatively is easier to implement, but again the problem is it's not suitable for all kind of applications. So this is a many-to-one mapping. Now there's one more which is kind of a hybrid, where we have many to many. So it's something like this. We have we will have Kernel also supports a number of threads, and it's something like they have this goes to. So maybe these two will be mapped to this. This is mapped to this. So this is mapped to this. Something like this. So maybe these two will be mapped to this thread, kernel thread. This will be mapped to this one. This will be mapped to this. So it's kind of a hybrid between one-to-one and many-to-one mapping. Okay. This kind of so here we have many user threads. They are mapped to many kernel threads, and some Unix and Windows supported by some Unix and Windows versions. The advantage is it's flexible. So OS creates the threads according to its own requirement. So this is the main advantage of this. OS, it creates kernel threads as required. And similarly, process also creates threads according to its own need. So process creates threads as required. So this is the advantage. However, it's a very complex because as you can see, we have double management. So it's very difficult to maintain. So this is the problem with the many-to-many mapping. Okay, so with this, we come to the discussion of threads. And now there are a few questions that need to be answered, or it remains now while discussing about threads, certain problems that need to be identified and should be highlighted, because these are the problems that come up while working with threads. And some of the questions that we like to ask is, say, suppose we have a process that has created a certain number of threads, and one of the threads has fork. Okay, so now operations such as fork, it becomes tricky to handle in multi-threading environment. So this is something that becomes difficult to handle. Why? Because the question is, when some thread forks, we know that when a process forks, a child is created. The question that comes up is, when we fork a child, okay, will all the threads be forked, or the thread that has invoked the fork will be forked? Which means, so if say there is a process and we have a certain number of threads, and one of them has invoked a fork, will this give rise to only the child arising out of this thread, or all of them will be fault? So that's a question that needs to be answered. And different OS, they handle it in different way. So there is, these are some of the problems that do come up. And the second problem that we'll be talking about in maybe the next lecture is, now when multiple threads, they happen to interact among themselves, a problem that comes up often is called race condition. Now this is a problem when multiple threads try to access a shared data or a data structure. And the problem that happens is, since all the threads, they would like to access the same data, at the end of execution of all the threads, the result is ambiguous. You're not sure what the result would be. There can be multiple results which may come out. Okay. So that is a problem that happens when multiple threads try to access the same data or a shared data structure. We'll see how we can overcome this race condition by proper synchronization of threads, and we'll talk about that in the next lecture.